Hello everyone, this is Dr. Nimish Kumar Srivastav, and in this lecture series of optical communication having a code of KEC 058. So I'm assistant professor in Ajay Kumar Garg Engineering College, and we are going through all the lectures associated with the optical communications. So in this today's video, we are going to discuss about the one most important testing equipments that is used by any optical engineer, that is optical time domain reflectometer. So this optical time domain reflectometer, we can see that it is something like a optical radar. So what is happening with the help of a normal radar? In a normal radar, what is happening? A radar is incidenting its pulse. It is sending a pulse, and that pulse, after striking that target, will be scattered back and move again in towards the radar. So at once it is moved toward the radar and it is received by the radar system. So it will move. It is having a basically it is having a coupler. So after that coupler will move it toward the receiver section. So now that receiver section will do the performance analysis. That means it will check what is the, with the help of its further circuitry, it will check what is the distance, what is the time taken by the pulse to move towards the target and again come back and received. So it will calculate the range at which your target is. So that is used for, that is the basic principle of the radar, finding the range of the target, at what distance a target is there. Even nowadays one can also find the speed with which that particular thing is moving. Very high accurate radars are available. So similarly to that, we are having a we are having a OTDR, optical time domain reflectometer. So in OTDR, what is happening, as it is used, it is called as optical radar, means that it want to check some performance, we want to do some performance analysis. And in that performance analysis, what is happening, it is a very versatile instrument, portable instrument, very versatile portable instrument, which is used to calculate what are the losses happening in the optical fiber. So it is a portable instrument used for identifying and locating the faults with what faults happening in at the connector side. I mean, if there is some mismatch between the optical fibers at the connector side, so what will happen? Some loss going to occur. So what is that loss? At what point that loss is occurring? At what distance that connectors is there from the transmitter side? One can easily find it from the optical time domain reflectometers. So it is used for locating the faults within a link. This instrument measures parameters such as attenuation, length, optical connectors and splices loss, and light reflectance levels. So whenever it is going to incident some light, and after that it will measure the time taken for the light to move back at its receiver terminals of the OTDR. So it will somehow do some performance evaluation, and will exactly find the location at which fault is occurring. So OTDR is fundamentally an optical radar which operates by periodically launching narrow laser pulses into the fibers. So by launching a narrow laser pulses into the fiber under test by using either a directional coupler or a circulator. These properties of an optical fiber link then are determined by analyzing the amplitude and temporal characteristic of the waveform of the reflected and the back scattered light. So OTDR basically consisting of a light source and a receiver, as well as the data acquisition and data processing modules. So what will happen? An information storage unit will also be there for retaining the data either in the internal memory, or some external memory facility is also provided to the with that OTDR module. and there will be some screens for visualizing the reflections. So now next thing is, this is the figure that is showing the trace of the backscattered and the reflected optical power as on the screen of the OTDR, and the meanings of the various traces and features we will see in the subsequent slides. What is the meaning of this dynamic range, and apart from that, what is this spikes that is occurring, and back scattered at the front connections, at the what are the connector losses, fiber and reflections, noise, power levels. We will see it in the coming slides. Now the next thing is that what is the informations that one can get with the help of that graph, this graph. What is the information that one can get on the horizontal axis? We are seeing a distance of the fiber. What is the distance along the fiber, that at what distance that loss is occurring. So we are having a calibrated distance along the fiber on the x-axis, and for a y-axis we are plotting the optical power level. So what is that power level with which a optical signal is coming back after scattering from a particular point at which a loss is occurring. So it will do the processing performance and will locate you at this distance, this some kind of a loss. Go and check this loss to overcome that performance degradation. So after this, how it is managing this thing, what is the conclusion we can draw from that particular figure, is the scale of the vertical axis. Scale of the vertical axis is logarithmic and measures the returning signal in decibels. So it will measure all the signals in the power level in the dB. Horizontal axis is showing the distance between the instrument and the measured point in the fiber. Because if you able to just locate the distance between the measured point, measurement point, and the instrument at which it is placed, so you can easily locate that at this distance there is some kind of a fault, and you can inform to a particular technician that go and just remove that fault, so that we can get the maximum the performance. Now the backscattered waveform has 4 distinct features. What are those distinct features? We have saw some spikes that was occurring in that reflection or a backscattered light that we are getting. So there are 4 informations that one can get from the backscattered curve. So the first information is a large initial pulse resulting from the Fresnel reflection at the point at the input end of the fiber. So a large initial pulse basically the large initial pulse that large spikes that is we can see is because of the Fresnel reflection at the input end of the fiber, this one, right? Now after this, what is happening? A long decaying tail resulting from there is a long decaying tail which is due to the Rayleigh scattering, right? A decay tail is there, this one. This large reflection is there because of the large scattering is there. Spike is there because of the Fresnel reflections. Then a decay is there because of the Rayleigh scattering in the reverse direction as the input pulse travel along the fiber. Abrupt shift in the curve caused by there is abrupt shift also there. How that abrupt shift is occurring is because of the optical losses as joint or connectors in the fiber lines. We are establishing a long optical fiber link by using a connector. Large number of connectors are there. So that connector also must be having some kind of a mismatching, or even because of the dirt that get deposited on the face of connector or on the tip of the fiber, there will be some loss that will happening in the power that is going to be coupled inside the fiber. So that power can be easily determined, that loss can also be easily determined by using a optical time domain reflectometer. So this point is showing that the abrupt shift, like this point, abrupt shift, this one. So this abrupt shift in the power level is basically because of the optical loss that is occurring at the joints and at the connectors in the fiber line. Now the next thing is there is a positive peak also, right, like this one. That positive peak arising from the Fresnel reflection at the far end of the fiber and at fiber joints, and because of the fiber imperfections. And fiber imperfections arises in the cylindrical structure of that fibers. Because of that, some imperfections arises, and even because of that imperfections, some reflections will be there, some positive spikes will be there. So this is complete figure showing the what are the different scattering that is happening. This sudden spike is there because of the Fresnel reflections, then degradation is there because of the Rayleigh scattering. After that, that is moving again forward, and there is a again spikes is there. This spike is showing that the loss, optical loss, which is associated with the connectors. After this, there are also some joints there because of the process called as a splicing. Some splicing process is also done. If suppose that we want to establish a link for 1000 kilometer, so that 1000 kilometer fiber is not available with us in a direct spool. One spool we cannot just wander around that fiber. So the standard length of a spool is around 15 kilometer or 10 kilometer or even 20 kilometer. So in order to connect a transmitter and the receiver that are 1000 kilometer apart, we have to connect various fiber spools. So that fiber spools can be connected with the help of two fibers can be joined with the help of a splicing process. So that splicing process also leads to some loss, because if some in the process of splicing, if you have not properly done the process of splicing, even then it's going to be that means because of the imperfection or because of the some man-made fault, you can also introduce some optical loss. That means sorry, that means core of one fiber not going to be perfectly aligned with the core of the another fiber. So if a core is already not perfectly aligned, then how you can assume that all optical power will couple into the another fiber? Some power will move to the cladding of the second fiber. So this leads to a loss of a optical strength. So that is also coming under the portion which is called as a splicing loss. So that splicing loss also can be directly measured by using a OTDR. This one, this is indicating a loss because of the splice, or this is also indicated even if there is some kind of a fiber bends, that whenever you are laying the fiber along under sea or even a long distance, there might be some curve that arises. You have to move the fiber across some curves, so that there will be some bends that will be there will some bend that developed inside the fiber. Even because of that bend, if you have moved above the safer limit of the radius of curvature of that fiber, then definitely some power will move into the clad region. So that will also leads to some loss, which is called as a bend loss. All the losses can easily be measured by the optical time domain reflectometer. Now what is the thing that is associated with the curve? We have seen that there are two phenomena that is initially seen at the curve portion. One was the loss because of the Fresnel reflection, and the other portion because of the Rayleigh scattering. So these two principally produce the back scattered light. Because of these two phenomena, the scattering of a light is there, and that scattered light get back scattered, and it will be measured by the OTDR. So Fresnel reflection occurs when the light enters a medium having a different index of refraction. That means a light is entering into the medium having a different refractive index. So suppose that we are having two refractive index for glass and air interface. So when a light of a power P0 is incident to the interface, is incident perpendicular to the interface, then the reflected power can be easily measured by a formula which is P reference equals to P0 and square of ratio of refractive index difference and the refractive index addition of these two interface. if we are taking a fiber, then what is the refractive index of a fiber, and the refractive index of air, which is already 1. So n fiber minus 1 and n fiber plus 1 to the whole square, and if you are multiplying it with the light of power which is incident perpendicular to the interface, you will get the reflected power. What is the amount of power that is getting reflected? Next thing, the detection and the measurement of an event depends upon the signal to noise ratio that an OTDR can achieve at that point. The signal to noise ratio is very important point, because you can recover back your original signal if the signal to noise ratio of that at the receiver side of that signal is very high. By saying that signal to noise ratio is high means that the strength of noise will be less and the strength of the signal will be high. So if the strength of the signal is much higher than the strength of the noise which is superimposed on it, then obviously you can separate out these noise and the signal from each other, and you can recover back the information content present in that signal. So that is the thing, and this is defined as the ratio between the back reflected signal and the noise level. So the signal to noise ratio depends on the various factors such as the OTDR pulse width, how often the OTDR samples the signal, and the distance to the measurement point. So this SNR depends on all these factors. Measurement point. Now the two important performance parameters to just evaluating the performance of your OTDR is dynamic range and the measurement range. Now the thing is, what is dynamic range and what is measurement range? Dynamic range is defined as the difference between the initial back scatter power level at the front end connector and the noise level peak at the far end of the fiber. So that difference going to give us the dynamic range of the OTDR. Again, it is the difference between the initial back scattered power level at the front end connector and the noise level peak at the far end of the fiber. Let us try to see it with the help of this diagram. So that difference between the values, this difference, peak value, and this one, the noise level, going to give us the dynamic range of the OTDR. Now after this, the dynamic range, what information one can derive from the dynamic range is that it provides us the information on the maximum fiber loss that can be measured and denotes the time required to measure a given fiber loss. Now the next important parameter associated with the OTDR is the measurement range. First parameter we have discussed is the dynamic range, and another important parameter is the measurement range. Now this measurement range, it deals with how far away an OTDR can identify events in the link. What events? Events like splice point loss, connection points, or fiber breaks. So all these things can be measured with the help of this parameter, that means measurement range. So it deals with the how far away an OTDR can identify events in the fiber or in the link, such as a splice point, connection points, or fiber breaks. Even if there is some kind of a break in the fiber, that range can also be measured with the help of OTDR. And the maximum range, Rmax, depends on the fiber attenuation, and on the pulse width. That is, on the dynamic range, which is denoted by DOTDR, if the attenuation is given by in dB per kilometer, then the maximum range in kilometer can be easily find out by Rmax is equal to DOTDR divided by that attenuation factor alpha. DOTDR is the dynamic range of the OTDR dividing by the attenuation factor. You are getting back the range at which, or the distance at which the thing is occurring, that loss is occurring. So you can easily find out those distances. So these are some important parameters that is used to evaluate the performance of the OTDR. So this is the basic diagram, the reflection points, what are different reflection points, giving us what is the information given by different reflection points is and the two important parameters that is used to evaluate the performance of the OTDR is dynamic range as well as the measurement range. Dynamic range is the difference between the maximum power of the first maximum backscattered value and the noise power level at the far end. So that difference give us the dynamic range or of the OTDR. That the what is the range of the OTDR to measure all those reflections, all those power levels, is something can easily be determined by this dynamic range. Another thing is the measurement range. What is the distance at which if some connector loss, if some splice loss is occurring, then what are those distances which can be easily measured by the OTDR. So that can be easily determined by the range, measurement range. So with this all this information we can just go through this OTDR and we can easily write it if suppose this is asked in the semester. So with this we will end this lecture series of this that means end this lecture video, and we will meet in our next video lecture with another topics. So thank you all. We will meet in our next video lecture.